Hello, you can hear me okay? Okay, so welcome to the second day, first session, the plenary one. And we have two speakers, Professor B.C. Joshi, who will be talking about ultra-long wavelength gravitational waves and the direction of nanohertz gravitational waves by the IPTA. And second talk will be on fast radio burst by Professor Marti. So both talks will be 40 minutes each, and please, I'll be taking questions at the end of it. So I think we can get started with Professor B.C. Joshi.
ನಿಮಿಷ ಪೋಡಿಯಂ ಆನ್ ಮಾಡಂಗೆ.
Good morning, everybody, and thanks to the SOC for giving me this wonderful opportunity to discuss some of the recent results from the pulsar timing array experiments. How do I change the slides? Okay. I am giving this presentation on behalf of the Indo-Japanese Pulsar Timing Array Collaboration, or the INPTA, which is a multi-institutional Indo-Japanese collaboration with about 40 research scientists as members from various institutes which are listed here. And at the outset, I would like to express special thanks to our European colleagues in the European Pulsar Timing Array Collaboration and the engineers and staff of the upgraded giant meter wave radio telescope, and in particular the telescope operators which made possible this almost decade-long monitoring campaign which the INPTA experiment actually uses. So a little historical note on gravitational waves. About 328 years elapsed for the discovery of gravitational waves after Newton first proposed action at a distance to define the gravitational force. But James Clerk Maxwell in 1864 actually wondered, even before Einstein, about the existence of these gravitational waves, invoking the inverse square law dependence implicit in such kind of fields in his landmark paper on electromagnetic theory. At the same time, Oliver Heaviside, a brilliant electrical engineer, actually worked out this complete analogy in this paper in Electrician, where he showed that gravitational waves must travel at a finite speed of light, much before the advent of the special theory of relativity by Albert Einstein in 1905. Soon after, Henry Poincare, in a paper, proposed retarded potentials to actually establish this kind of a conjecture. As far as Einstein is concerned, he himself did not believe in gravitational waves when he proposed the general theory of relativity. But by 1918, he had written a paper discussing various aspects of these gravitational waves, only to repudiate this paper in 1936. And it took about 20 years since that time for Bondi, Pirani, and others to establish these theoretically, and another 60 years for advanced laser interferometer gravitational wave observatories, or advanced LIGO, to make the first direct detection. Now, gravitational waves can be generated by motions of masses or mass distributions, and the conservation of mass and linear momentum implies that the time varying quantity responsible for gravitational wave radiation is the changing quadrupole moment of the mass distribution. In vacuum, if you take the Einstein's equation and use the linear approximation, one can show that these equations, they reduce to a plane wave equation if you consider a very tiny and small perturbation in metric. And one can show that these are transverse waves with two polarizations of the type which are shown here. For a circular binary, the gravitational waves emitted are emitted at twice the orbital frequency or orbital period because of the quadrupolar nature of these gravitational. Now, any motion of collection of masses can produce gravitational waves, but for the purpose of this talk, there are four broad categories of gravitational wave sources that are expected to be detected, which are shown here. Coalescing compact binaries like the neutron star, and black hole binaries, or supernova explosion can produce short duration but intense gravitational wave sources, which are the ones here. On the other hand, gravitational radiation dominated evolution of the compact binaries can produce long duration continuous gravitational waves. And if one takes a superposition of large number of such continuous gravitational wave sources, you get what is known as stochastic gravitational wave background, and that's the background which we will be talking about today. The gravitational wave spectrum itself is likely to encompass about 22 orders of magnitude from attohertz to about kilohertz. The advanced LIGO discovered gravitational waves in the high frequency band due to the short transient sources, but the low frequency or ultra long wavelength gravitational waves are as yet to be detected. And a promising wave band here is the ultra low frequency wave band where the PTA experiments operate, and I'll be talking about those today. Now, gravitational waves can be detected by measuring the variation of proper distance between two different points. And this measurement of variation can be done, for example, by estimating the shift in fringes due to changes in arm length of an interferometer. And this is the principle on which the advanced LIGO works. But the arm length of a LIGO terrestrial detector is of the order of 4 kilometers, so they are sensitive to shorter wavelengths or higher frequencies. Propagation of pulsed electromagnetic signals from celestial clocks, called radio pulsars, provide an alternative yet a very, very precise way for measurement of the variation of proper distance between 2 points. And because here we are talking of a galactic scale detector with wavelengths of few parsecs and frequencies of the order of nanohertz, you have a very long timing kind of an experiment to do this. Okay? And pulsar timing array are experiments to do precisely the same kind of thing, where you use a collection of widely separated pulsars distributed uniformly across the sky. Because of the periods of the gravitational wave involved of the order of a decade or so, PTA experiments by design are decade-long experiments. The main component of a pulsar timing array is a radio pulsar, which are highly magnetized rotating neutron stars, which are massive and compact, storing an immense amount of rotational kinetic energy. Very little of this energy is lost in the radiation and particle winds, and this means that they have a very precise rotation and pulsation and provide the best celestial clocks for doing any kind of gravity experiment, including the detection of gravitational waves. The relatively smaller magnetic fields and shorter periods for pulsars known as millisecond pulsars, which are shown here in the left bottom corner of this PP dot plot for the pulsars, are the most stable clocks, and therefore they provide the best available galactic clocks to detect gravitational waves. Now, the measurement of the pulsation frequency of this pulsar is done by a technique known as pulsar timing, which is schematically shown here, where the prediction of the pulse time of arrival, or TOA, from a rotational model of the star is compared with the observed time of arrival by keeping track of the number of rotations of the star. So, the predicted and the observed ones are in blue and red, and because this prediction is compared, you take a difference which is known as timing residuals plotted here. It grows with increasing time baselines, which allows for very, very high precision measurements of the pulsational frequency for doing these kind of things. Now, the pulsar timing model itself is fairly complicated, and amongst other things, it consists of rotational, astrometric, the interstellar medium, binary and dynamical parameters. The system, if there is any sort of unmodeled effect in this timing model, that appears as a systematic, it manifests as a systematic in the timing residuals. And gravitational wave can also be a systematic in this timing residuals, which appears as a time correlated red noise signals in the timing residuals. And the aim of the PTA experiment is to actually measure this with high precision pulsar timing. Now, there are lots of challenges and there are lots of uncertainties. The better the timing model, the higher is the sensitivity to gravitational waves. And one of the uncertainty in making such precise measurement is our own imperfect knowledge of the solar system dynamics. This creeps in the timing as a unmodeled systematic, and as an illustration, a very small error in the masses of the outer and inner planets can actually lead to a growing sort of systematic, which is orders of magnitude larger than the expected gravitational wave signals. So, one needs to actually have a precise ephemeris of the solar system in order to be able to do that, and for almost a decade, this was a major challenge in detection of the gravitational waves. Another challenge which is there is in terms of what is known as achromatic spin noise. Okay. This is essentially a stochastic wander in the rotation rate. So, I said pulsars are good clocks. They are actually phenomenal clocks, but nevertheless, most pulsars show a random wander in the rotation rate over months and decades. And this is just an example from one of our earlier works for pulsar B0534 plus 2200, where you see that the rotation rate is actually changing in a very unpredictable and stochastic manner. Okay. The time scale of this is more or less similar to the time scale of the gravitational wave, which one is trying to sort of extract out. And the amplitudes is again 3 orders of magnitude larger than the gravitational wave. So, that is a major challenge to be taken into account. A third challenge is the propagation delays. So, the pulse propagating in the ionized interstellar medium is dispersed by tenuous electron plasma, and it is also broadened because of multipath propagation in the ISM with the frequency dependence of this kind of a thing. And this basically leads to a delay in pulse TOA at lower frequencies. And this delay is not constant. It varies over months and years, as can be seen from both these plots. These are dispersion measure or measure of the dispersive delay varying over a period of time over almost 4 years or 6 years. And similarly, the scatter broadening varying for a given pulsar. Again, the time scale of variation is similar to gravitational waves, and the amplitude is about 3 orders of magnitude larger than the gravitational wave which one is trying to extract. So, these are the challenges which we should keep in mind, and I'll have something to say about it a little bit later. So, in principle, since pulsar is a fantastic clock, you can use it for detecting gravitational waves, and you do it because the apparent frequency of pulsar clock varies due to perturbation in metric by a passing gravitational wave with an expected amplitude of the order of log amplitude of the order of -15, which, as you can see, is 3 orders of magnitude lower than the effects which I talked about. So, in principle, you can detect gravitational waves by doing precision timing of a single individual pulsar. But in practice, there is large frequency variations which happen because of the rotational rate variation and the variation in the propagation effects. So, doing this with a single pulsar is not a very useful thing. In contrast, a passing gravitational wave imprints systematic in the timing residuals of a pair of pulsars which are correlated. So a better method is to use correlations amongst pairs of pulsars, and this correlation, because of the quadrupolar nature of the gravitational wave which we are trying to detect, this correlation has a form of this type for the given geometry, or plotted as a function of angular separation between the pairs, looks something like this, and this is known as Helings and Downs overlap function. Okay. So PTA experiments are experiments which use a collection of pulsars to detect these spatial correlations for finding out the gravitational waves. Now, this correlation is produced by gravitational waves from supermassive black hole binary systems, which reside at the centers of the galaxies, which we know are there. In fact, one of the images here is something like that. So, essentially, the supermassive black hole binary systems will form from mergers of galaxies. And from the hierarchical clustering models of evolution and formation of the galaxy, one knows that the dynamic friction in the merging galaxies drive the host black holes of these two galaxies together to form a supermassive black hole binary systems with orbital periods of years and decades. So that is the signal which one is trying to look for, and again one is looking for this because this dynamical, the late time evolution of this supermassive black hole binary system is gravitational radiation dominated, where the frequency of the emitted gravitational wave slowly increases as the gravitational radiation shrinks the orbit of the supermassive black hole binary systems in a phase which is this lasts for several hundreds of millions of years. So you get a continuous gravitational wave from that, which is precisely in the frequency band of the pulsar timing array experiments of the order of nanohertz. However, okay, I can't go back. Okay. So, however, the signal from an individual source is too weak to detect. So, what one is trying to look for is an incoherent sum of the gravitational waves from an ensemble of these supermassive black hole binaries, or in other words, the stochastic gravitational wave background which I talked about earlier. Now, in actual practice, the important thing to realize is that a supermassive black hole binary which has a large orbital period will evolve relatively slowly as compared to that which has a short orbital period. Now, this difference in the residence time between the orbital period bin means that there is a larger number density of the supermassive black hole binaries in the large orbital bin, or consequently small frequency bins, than in the other case, and that endows the stochastic gravitational wave background which we are trying to look for, a characteristic spectrum which is shown here with an index of the order of -2/3 for the characteristic strain and an index of 13/3 for the other particular case. So, is there a way I can go back? Because this will be a bit annoying. Okay. Yeah, thanks. So you should get this dashed line, which is the which is with this particular spectral index, and that is the spectrum which one is trying to detect. We are not looking for individual supermassive black hole binary in the first place. We are looking for a stochastic background which has a given characteristic spectrum. So the main object in the last 2 decades for pulsar timing array experiment has been to detect a power law spectra with a 13/3 spectral index, and as I mentioned earlier, a Helings and Down spatial correlation. And this is being done by 4 major regional pulsar timing array experiments: the European pulsar timing array, the Indo-Japanese pulsar timing array, the North American nanohertz observatory for gravitational waves, and the Parkes pulsar timing array, which have time baselines ranging from about 7 to 24 years, consisting of a pulsar sample of about 20 to 67 pulsars. All these experiments routinely make public releases of their data and then combine the data together in what is known as International Pulsar Timing Array Consortium, or IPTA, which is the most sensitive PTA data set for detecting gravitational waves. In the last 4 or 5 years, there have been 2 emerging experiments which have got added. One uses the Meerkat telescope in South Africa, and the other one uses the FAST telescope in China called the CPTA. So our experiment, the Indo-Japanese Pulsar Timing Array experiment, is a collaboration of 40 scientists which observes 22 pulsars routinely once every 14 days. And in this experiment, we use the unique subarray capability of the upgraded giant meter wave radio telescope to make 2 co-located 75-meter telescopes for concurrent 300 to 500 and 1260 to 1460 megahertz observations of these 22 pulsars once every 14 days. This niche capability of the UGMRT means that we are the only PTA amongst the PTA experiments which can provide precision DM measurements and characterize the effects of interstellar medium for detection of the gravitational waves, and that's our key contribution to the detection of which I am going to talk about a little later. We made our first public data release in 2022, led by a team by Pratik Tarafdar, and some of the members who are shown here made major contributions to this, where we also made the first public release of the high precision DM time series. And because of the unique capabilities of the UGMRT, we were able to achieve unprecedented DM precision in the history of pulsar astronomy, 1 part in 10 to the power minus 6. No such precision measurements have ever been obtained by any other telescope. And that is sort of schematically shown here. And we released this as part of the IPTA process and also combined it, as I will mention later on, with our European colleagues. Our European colleagues in EPTA used Europe's 5 most sensitive telescopes to observe 25 pulsars over the last 25 years using frequencies between 1 to 2 gigahertz. And this data was analyzed in 2 parts. One was DR2 full, which used the full time baseline of 25 years, and the other one was DR2 new, which used a time baseline of 10 years, but the newer backend and instrumentation in these telescopes. The former is very good with its long time baseline to constrain the rotational, astrometric and other parameters of the timing model, which I said are very important for sensitivity of the gravitational waves, whereas the latter data set was much more sensitive because of the new instrumentation and the less systematics in that. Now, one thing to note is that we in PTA lacked a long time baseline. Our baseline in the data release was of the order of 4 years. EPTA, on the other hand, could only observe above 1 gigahertz, so they lacked low frequency coverage. Low frequency, where the ISM effects are strong functions, are very, very strong and dominant. So because of this, there was a very good fit between INPTA and EPTA data sets. And since they complement each other very well, we decided to do a joint analysis for looking for the gravitational waves. One of the things which was new in this particular analysis as compared to the past efforts was the use of more advanced noise models. I have already hinted to you the noise sources with which we are affected, the ISM noise, the spin wonder noise and so on. We used a Bayesian analysis of the timing residuals to try and model this with hyperparameters and subtract it away from the residuals to look for the 3 orders of magnitude smaller gravitational wave. 3 different time correlated noise models were used: achromatic spin noise, a chromatic DM noise with a radio frequency, observing radio frequency dependence of nu to the power minus 2, and a chromatic scattering noise, which was never used earlier, with a dependence of nu to the power minus 4. And each of these noises were modeled in the spectral domain as a power law with 2 hyperparameters, its log amplitude and the spectral index gamma. Aman Srivastava from INPTA led this analysis, and those of you who were present yesterday would have heard about the details of this analysis in his talk, so I will not go into that, except for pointing these two plots out here. This is from the NPTEA data release for a pulsar J19 39 plus 21 34, and these are the noise models. This is the log amplitude and the gamma for the achromatic spin noise. The middle ones are the posteriors for the chromatic DM noise, and the last one are the posteriors for the chromatic scattering noise. It's worth pointing out that these two models could be constrained only because of the low frequency, the unique low frequency nature of the NPTEA data sets. What addition of this data had to the EPTA plus NPTEA set can be actually seen from this plot, where the gray posteriors are the posteriors from the EPTA alone data. But when you add the NPTEA data to joint EPTA data, you get the blue posteriors. And one can see that the noise models are much better constrained and the noise parameters are much better known. And that was one of the contributing factors in extracting higher sensitivity in the NPTEA plus EPTA joint data sets. So when we analyze this data set, this is what we get. As I mentioned earlier, for detection of stochastic gravitational wave background, two criteria are needed. One is the spectrum with the spectral index of 13/3, and other is the Hellings's and Downs spatial correlation. The plot on the right shows the amplitude on the y-axis and the spectral index on the x-axis, and the contours are the posterior distributions. The solid line is the 13/3 expected spectral index if the background is entirely made by the continuous gravitational waves from an ensemble of supermassive black hole binary systems. The plot on the left shows the posteriors as violins for pairs of pulsars and compares it with the solid line, which is the Hellings's and Downs spatial correlation, and it agrees at 95% confidence with the presence of the gravitational waves, and together these two plots give a 3.5 sigma detection in the DR2 nu plus data set, which is the EPTA plus NPTEA combined data set. However, one thing to note is that these posteriors are not exactly lying on this dotted line of 13/3, and there seems to be a mild tension, and I will say something more about it a little later. The other experiments also simultaneously in a coordinated fashion in June 29th released their results. The top results are from the nanograv PTA analysis, which is very similar to our results, and the bottom one is from the Parkes pulsar timing array. The results are consistent with us except for the fact that the nanograv has a slightly higher significance of 4 sigma, and the PPTA has a smaller significance of 2 sigma in the detection of the stochastic gravitational wave background. A very quick combination of all of these data sets is instructive to see for looking at the consistency. What is plotted here are posteriors for the common correlated red noise for different PTAs in different colors, over plotted by these black contours, which is a very quick and dirty combination of data sets together, and it illustrates that the posteriors are very consistent with each other. So these results are consistent, and when you add all of them, you expect the significance to go even higher. And some of the NPTEA members played a very crucial role in comparing these posteriors. I have highlighted our PhD student Subhajit Dandpat, who actually worked in comparing many of these posteriors here. So basically that is the result, that we have detected the gravitational waves at the low frequency end and opened a new window in the gravitational wave spectrum. But what are the implications of these results? The first thing is to look for the origin of this stochastic gravitational wave background. Is it because of supermassive black hole binaries? So to test that, our collaboration actually did simulations with 100 realizations of about 3,240 models. Each of these models had different prescriptions for what happens to the dynamics of supermassive black hole binary before the merger, whether the accretion happens on one or on the other, with the revised supermassive black hole binary galaxy scaling relations, and more importantly, invoking different eccentricities in these binary systems. And what we find is that our results, which are the orange violins in these plots, are consistent with what we get for simulations of these 324K different models, which are in the green violins. We also see that given this background, we have a 50% chance of detecting an individual supermassive black hole binary system at low frequencies. And I'll talk about it a little bit later. A look at the nanograph result is also instructive. There, the data, which is the green, is not really overlapping with their simulation. But one thing to note is that they used a different simulation code than what we used. And more importantly and crucially, they did not have eccentricity baked into their simulations. So they only assumed circular binaries, and the tension is much larger than what it is in this. But nevertheless, these two results do point out to the fact that supermassive black hole binaries producing a stochastic gravitational wave background may not be entirely a true story, and that is something to keep in mind. Of course, this tension should be treated with caution because it could also come by statistical bias, and we explored this in one of our papers by assuming an ideal PTA and injecting a real 13/3 stochastic gravitational wave background, and then recovered it in presence of noise models which were borrowed from the EPTA plus EPTA noise models. So we took the actual noise models, added it to a 13/3 spectrum in an ideal PTA and tried to recover, and these are the results. And again, you can see that the posteriors don't sit exactly at this dot where one would where the injected signal was there. So this cross shows you the injected signal, and one would expect the posterior sitting right there, but it does not sit there, which sort of tells you that the tension in the recovered signal may purely be a statistical bias, and one must not jump into an astrophysical interpretation without sort of worrying about this issue. Maybe higher signal to noise ratio is required. Nevertheless, this tension means that we have to think about backgrounds beyond the supermassive black hole binary systems, and I have listed a few cases here with the caveat that I am not an expert in any of these kind of things. These are only listed here because I feel follow-up sort of work is needed by anyone interested in some of these. And again, since I am running out of time, I will not go into the details of that, except to say that our data is actually consistent with a stochastic gravitational wave background which is produced by any of these cases. Okay. So the data is not informative enough to discriminate between a stochastic gravitational wave background, which is due to the incoherent sum of continuous gravitational waves from a large number of supermassive black hole binary system, or due to inflationary gravitational waves produced in the era of inflation, or due to collision of bubbles nucleated in phase transitions, in cosmological phase transitions, or release of gravitational wave energy by cosmic strings and domain walls and so on, or for that matter ultralight dark matter with scalar field with a mass of the order of 10 to the power minus 22 and minus 23 electron volts and so on. So any of these scenarios can produce, by some tweaking of the parameters, the stochastic gravitational wave background. However, what is interesting here is you may not be able to discriminate, but you can put useful and interesting constraint on parameters of these models. And some of that are there in these papers which I have sort of listed here. I will not go into the details. Now, right now what we are doing is, after June 29th, we are adding the data together, and a quick addition already in different orders of the PTA shows that we should be able to achieve about 5 signal to noise ratio from the combined data set. But this should be taken with caution because here the noise models used by different PTAs were different and some of them were in tension. So it may be 5 sigma, it may not be 5 sigma. So a more systematic combination is currently in progress. On the in-PTA front, we are proceeding by developing newer techniques to improve the sensitivity of data to gravitational waves. And one such technique was recently sort of submitted by one of our members, Jaikhomba Singha and his team, where we are trying to remove the bias which is seen in the estimation of dispersion measure because of variable scatter broadening in the data. So we use this particular thing to remove the bias, and that is the technique which we have shown on some of the pulsars, and that would remove the scattering noise from the and make the data more sensitive. Another interesting thing which we are actually doing is to characterize pulse jitter, which is a white noise due to pulse shape fluctuation. And another team by our member Tomanosuke and others have shown that this jitter actually reduces at low frequency, opening up a very interesting possibility of a large sample of pulsars to be used in a low frequency alone PTA. So these are the two main things which we have just finished, and right now we are in the process of preparing what is the InPTA public data release 2, and which has a time baseline of about 7 years with a number of pulsars of 29 with very high precision DM time series for the first time over a period of these 7 years, and this is just an example of 1909. The team is led by Dr. Prerna Rana and Neelam Dhanda, along with others who have been shown there in that particular slide. Last but not the least, most of our work in the last 2 months have been going on in what we call as the International Pulsar Timing Array, or IPTA, Early Data Release 3 or DR3, and this promises to be the most sensitive data release ever and is likely to probably exceed the 5 sigma. The early indications are that it will exceed the 5 sigma detection threshold. And this is just an example for a pulsar J1909-3744, where you can see the long time baseline, the 24-year time baseline, and the really wide frequency coverage from 300 megahertz all the way to 4 gigahertz promises to give a very sensitive data set. The points in the blue are the InPTA points, okay, just for the reference in that combination. Okay, so this is my last slide. So while this is all very good, I think one thing which should be of interest to the wider audience here is that with this particular discovery, we have opened a new window of gravitational wave astrophysics. But for this field to grow, it requires inputs from diverse areas of astronomy, and some of those I have listed here. Some of these inputs are useful for the PTA experiment itself because they improve the sensitivity of these experiments to gravitational waves. On the other hand, the increased sensitivity will produce new results which would be of interest to these diverse field of astronomy and so on and so forth. In particular, the point 1 and 2 from the solar system dynamics and the solar physics point of view are important inputs which would help in improving the PTA sensitivity. 3 and 4 are the points from the basically galactic distance measurement, either from Gaia or from VLBI, which are very important to get pulsar distances for detection of individual supermassive black hole binary system. And that is the next milestone as far as the IPTA experiments are concerned. And for that, we need distances very accurately. And also to find the suitable targets for the gravitational supermassive black hole binary gravitational wave emitting sources, we need sources, extragalactic sources like X-shaped sources, observations of that, or periodic variability in blazars and modeling to show that these are supermassive black hole binary systems. Of course, the increased sensitivity and the new results will also feed into the galaxy evolution models and also into the cosmology. So I will just end here, leaving my summary here that we have detected gravitational waves with 3.5 sigma evidence. Although we see a mild tension, which probably suggests that there may be other origins of the stochastic gravitational wave background, but the data is not discriminatory enough to discriminate between different theories. In the InPTA collaboration, we continue with developing new techniques for accounting ISM noise, and our second public data release is in progress, hopefully in the next 2 to 3 months. And a combination of data from all PTAs is in progress to get the most sensitive data set and a higher significance of gravitational waves. And as I said in the last slide, inverse inputs from diverse areas of astrophysics will really help flourish the gravitational wave astrophysics much more than what it is today. Thank you.
Yeah, thank you so much for the wonderful summary and the details. So we can take questions now. Yeah, just.
Yeah, wonderful talk, BCJ. Two comments. One is that in systematics, can we rule out, maybe this will require theoretical studies, systematic variations coming from the ISM itself over these time scales? Because the total volume which is being probed by these pulsars is not very large in terms of galactic scales. And it could very well be that there are long wave perturbations in the ISM which are modulating all of this. So has that been looked at?
No, it has not been looked at. Okay, so that's the short answer. As far as the usefulness of that, yes, it is tremendously useful. Some couple of decades back, somebody tried to do with pulsars itself. So now we know 3,400 pulsars as of today. So you can sample different lines of sights of the galaxy. You can get a picture of the dynamics of the ISM with that. But not just pulsars. You can use point extragalactic sources. You can use the refraction and the scatter wandering with small, say, LTA kind of observations. So it's certainly possible, but I think these kind of studies need to be taken.
The other is just a comment about some unpublished work done with our students at ISA Mohali. What they did was to look at the gravitational wave background which you get from sources within the galaxy. Okay, so these are Gaia binaries and so on. Of course, Gaia does not have sensitivity at the frequencies which we are looking at, so it looks at, we can look at somewhat higher frequencies. But there is a very nice power law background which emerges just from the stellar binary distribution, which is
so
not
that's very interesting. I didn't have time to go into that. There is also cosmic variance. The Hellings and Downs curve, which I said, is not a God-given straight line, solid line. There will be variance on that. That's called cosmic variance. And what Jasjit is pointing out, looking at these backgrounds modeled from a different perspective. So most of the galactic binaries will go into the LIGO band, but nevertheless, whatever we learn from that can also be incorporated in building the models which could be used.
Not in the LIGO band, they are kind of around.
So they are very, very wide binaries?
Yeah, wide binaries, you are looking
1 year,
at
2 year, 3 year kind.
Okay. You're looking at microhertz, not nanohertz.
Okay, so Lisa band. Nevertheless, the techniques are useful even for this, so that's certainly welcome.
Okay, so there's another question.
I think you mentioned 10 to the minus 10 solar mass will make a change, right? So unknown asteroids and maybe clumpy dark matters in our galaxy.
So I don't know how to go back.
No, but
so
that's
I can't take you to that slide, but there was a lower plot in that slide. And there is a paper by Guo et al. In 2019 for a planet lurking behind the sun. So you can actually, the precision in the pulsar timing is so high that you can actually, in a Bayesian way, infer unknown masses in the solar system. So they put a very interesting constraint on something which is lurking behind the sun. So you never see it, okay, but it is nevertheless there, okay. And so in last decade, this was the big challenge. So a lot of things, because the JPL is not able to provide us ephemeris as accurate as we need, so we have developed lots of methods to overcome those problems. Some of them can be applied to do exactly what you are saying, the inverse problem.
Also, clumpy dark matter, if there are.
Maybe I think we should go to somebody. We can talk offline, okay? Maybe last question from you.
So you showed this very interesting plot where there were 3,000 different prescription run 100 times, and then there's a posterior of that in green. So what I wanted to ask is if you can categorize those prescription in some physical categories.
Just a minute, let me, this is the one you are talking of, right?
Yes.
Yes.
So the green contour, it seems like some of the prescription is actually even further away from that black dashed line, which is the spectral index. And so those can be probably ruled out at 4 sigma. So have people tried characterizing this prescription in different category and see if any models can be ruled out?
Very good question, and I think that is some work which some of our collaboration members are doing, but it's not exhaustive. So as I said, there are a lot of details which I didn't have time to go through in terms of what kind of accretion is taking place during the merger process and so on. You can put very, very interesting constraints on each one of them and try and see how far it is. This was done in an average sense to get a posterior to see if there is a real tension or not. Okay. So maybe the knowledge of galaxy evolution is imperfect. We do not have a very good knowledge. So you use whatever is available from the astrophysics earlier, and maybe the 13/3 is not matching with that just because you don't have the right prescription. But just as he was asking, you can do an inverse problem and try and put interesting constraint on some of those parameters. Not all of these things have been looked at. So certainly it's worth exploring.
Thank you.
Okay, thank you so much. I think there are a lot more questions, I know, but we should catch him over the breaks, and let's move on to the next talk. Thank you so much, Professor Joshi. Once again. So next is Professor Marti. I think he'll be talking about fast radio burst.
Okay, am I audible? Fine. Okay, so good morning, everyone, and I thank the SOC for giving me this opportunity to talk about fast radio bursts. How things are working. Is there a different pointer? Okay, fine. I think this should be okay. Thanks. Okay, so again, thanks to the SOC for giving me this opportunity. Although I've been asked to give this talk about fast radio bursts, I wish to acknowledge the contribution from many of my collaborators who are listed here. Some of them have moved on to other places, but this was at the time they were at their respective places. And so, nowadays there are conferences dedicated to fast radio bursts. So within this half an hour or so, I'll try and do justice to this topic. So considering the wide cross-section of people in the audience, I'll try and give a very broad-based introduction and then focus on a few results that we have from the GMRT. Okay, so let me begin by giving an introduction to fast radio bursts. So let's ask the question, what are fast radio bursts? Okay, so it's customary to begin every talk on fast radio bursts by showing this wonderful picture. It's called the Lorimer burst. Okay, so this was discovered in 2007. This was part of some other data. I think it was part of some pulsar search data, I think, with Parkes, and this dispersed pulse was discovered. It was discovered in 2007 by Lorimer, Duncan Lorimer and his collaborators. So what does this show? So this shows the arrival of a pulse which arrives earlier at high frequencies and later at low frequencies, and that phenomenon is called dispersion. It's a propagation effect. It happens because of the ionized plasma. And dispersion is usually characterized by a quantity called the dispersion measure, which is defined as the line integral along the line of sight of the total number of electrons. So it's the electron column from us all the way to the object. Okay, and this was seen to be highly dispersed. So, and the dispersion measure was so large that it suggested that it's probably of possibly extragalactic origin. And since it was thought that this is extragalactic, it was recognized to be important for cosmology because it's certainly not coming from the Milky Way. And since its discovery in 2007, there's been an explosion in the number of FRBs, and FRBs is now, in its own right, it's a field in itself. And the current status is that there are about 800 fast radio bursts. Since in the last 10 years or so, that's the time scale, and we have about 800 fast radio bursts which are known. So why are these called fast radio bursts? They're called fast because if you look at the pulse duration, it's extremely sharp. It's very narrow in time, confined in time, lasting only hundreds of microseconds to about tens of milliseconds. And they're detected primarily in radio. They've not been seen in other bands, in other wavelengths. And it's called a burst because it's transient in nature. And it puts out a lot of energy, of the order of 10 to the 38 ergs within a few milliseconds. So it's very energetic, and that's why it's called a burst. Okay, so the field didn't move much in the first few years because, these were discovered on and off once in a while. And in 2014, everything changed because the first repeater was detected. Essentially, one of the fast radio bursts, which is called the 2012-11, was seen in the same coordinates with the same dispersion measure, and it was seen to repeat. So the same sky coordinates, same dispersion measure, it can't be from a different source. So that was the first repeater. It was discovered detected with Arecibo, and so that really transformed the field. Okay, so why did repeaters transform the field? So if something is repeating, you know that it can be detected, so you can reobserve them. You have a finite probability of detection, and they can be localized, which means that you can exactly point where they're coming from. And once you have a large number of bursts, you have a sample to study their statistics and look at their emission physics, what kind of progenitors cause these bursts, and you can study the intervening medium. And you can possibly also do some cosmology. Cosmology because they're thought to be of extragalactic origin, and there is a relation which predicts that based on the contribution to the dispersion measure from the intergalactic medium, you can actually do some cosmological inference. Okay, so why study fast radio bursts? As I said, currently we know about 800 of them, and 50 of them are repeating fast radio bursts. And I'll come to what are repeaters in a moment. So the main FRB engines, so to speak, the telescopes which have been detecting these FRBs and contributing to the population, the number of FRBs, are the CHIME FRB, which has been the most prolific one. And there's also ASCAP, which is in Australia. And then you have a few other telescopes which have also detected a few FRBs. So how to detect FRBs? So you can see that most of the FRBs have actually come from CHIME and ASCAP, and that's because they have a very large field of view, because FRBs are thought to be happening all over the sky. And if you want to detect as many of them, you have to be looking as large a part of the sky as possible. And so you need you need telescopes designed to detect FRBs. And that's what has happened with CHIME. So what can be studied with fast radio bursts? The astrophysical origin is still debatable. The emission physics is not known. There are some proposals now, and the field is sort of converging. And you can look at their statistical properties, their spectrotemporal evolution, their intrinsic polarization properties, and also propagation through different media, especially in the host galaxy. And then there's the intergalactic medium. And you may, by chance, encounter some intervening galaxy, and then you have the Milky Way itself. And the other question, which is not clearly the answer to the question, why only a small fraction of fast radio bursts repeats, is also not known. Well, so there are some proposals as to why that is the case, but that's still an open question. So what's a repeater? A repeater is one, as I said, which seems to be coming from the same source. So you know its DM, you know its position. So what's the difference between repeater and non-repeater? So these are observed differences between repeaters and non-repeaters. And it appears that non-repeating FRBs have they put out bursts with higher energy. So and that's sort of shown in this picture. So this is the energy versus rate function. And you can see that the higher energy FRBs are fewer in number. And so these are the non-repeaters, and the repeaters tend to have lower energy. Okay, so they're more numerous. And it's also, the non-repeater burst widths also tend to be much narrower than the repeater widths. The repeaters typically tend to be wider. And the non-repeaters also tend to be broadband emission, whereas repeaters tend to be narrowband. So these are some of the observed differences in between repeaters and non-repeaters. And repeaters also show something very remarkable. They sort of drift in frequency with time, and that's not seen with non-repeaters. Okay, so then the question is, why do we follow up repeating FRBs? What's the value in following up repeating FRBs? The one-line answer to that is repeaters offer a greater chance of detailed investigation. When you have a one-off burst, you might not have prepared for it, but once you know that a fast radio burst is repeating, you can train your telescope on that particular object. You can observe them for a long time. And the energy of the fast radio burst, of the order of 10 to the 38 ergs, suggests that the source of the energy has to be a coherent source. And although there are many models, initially there were many theories, there were many models for what causes FRBs, there is now some agreement that it has to, since we're talking about a coherent source, I have listed the two most popular models. One is called the concordance model. The other one is the magnetar, which itself is proposed to be the source of FRB. But you can see in both cases, you have a compact object here, typically a magnetar, and in the concordance model, you have some layers of either ionized medium or, if it's embedded in some supernova ejecta, which causes all the observed properties. So the models both of these don't satisfactorily explain all that is observed, but I think the field is also moving slowly towards explaining what causes FRBs. So the other usefulness of studying FRBs is that you want to study what the host galaxy looks like in optical and radio, and whether they are star-forming galaxies or irregular galaxies. And there's one FRB which has been seen in a globular cluster, and it was difficult to explain how an FRB could actually reside in a globular cluster. And you can also study the persistent radio emission because it has some connection to the origin of fast radio bursts. Again, whether it's coming from an AGN type or star-forming type galaxy or dwarf irregular galaxies, or if there are some kind of afterglow. So there's lots of things that can actually be done with FRBs. The other thing is, of course, you also want to localize FRBs, and there are a few FRBs which have been localized. Currently, I think about of the order of 10 FRBs have been localized. And instantaneous localization is now becoming popular. This is being done by deep synoptic array. So even if you have a non-repeater, you can instantaneously localize it. The other, and also there's also this other project which is happening at the GMRT. It's called Spotlight, which will also be able to instantaneously localize to arcseconds. So once you localize FRBs, you can follow up FRBs to study many things. One is, of course, as I said, the statistics. You can look at the expected distribution of FRBs. You can study the waiting times just to see how FRBs behave, and ask the question whether FRBs are truly random, or is there some underlying periodicity, because periodicity is important to connect them to, for example, magnetars. And you can also study propagation effects. The variation of the dispersion measure, rotation measure is another quantity which tells you about polarization. You can study the circumburst medium, the medium immediately surrounding the FRB. You can also study the local magnetic field or the line of sight magnetic field if you look at rotation measures. You can study scattering, which usually occurs closer to the host galaxy. And you can also study contributions to the scattering from the Milky Way. And you might encounter some intervening galaxy, and there's been some detection of intervening galaxy halo in this work. And you can also study scintillation, which I'll be talking about quite a bit later in the talk. So all these studies require a large sample of bursts spread both in time and frequency. So that's why, as I said, why follow up repeating FRBs? Because we need a large sample to do all these studies. Okay, and what are the strategies for observing repeating FRBs? Typically, once you detect FRBs with these large field of view telescopes like CHIME and ASCAP, you want to follow up repeating FRBs with more sensitive telescopes like the GMRT, which have a much narrower field of view, but they have a much better sensitivity than these telescopes. And you also have telescopes like FAST, which are even more sensitive. So these strategies, typically once you detect an FRB, you observe it at low radio frequencies, typically below 2 gigahertz, and then use sensitive telescopes mainly for their sensitivity and the wide bandwidths, which also offer the advantage of tracking them, because a telescope like CHIME is a transit telescope. You can detect an FRB only if it is inside your beam, and it does not track the sky. Whereas if you use a telescope like the GMRT or FAST or Effelsberg, you can track the sky coordinates from rise to set for a long time, so you have more chance of detecting more bursts from a repeating FRB. And what is also becoming more popular is a multi-wavelength follow-up campaign using different telescopes in different bands to study if FRBs seen in radio also are seen, this things like prompt emission at other bands can also be looked at in the follow-up studies. Okay, so with that brief introduction, I will talk a little bit about the main results from our GMRT observations. I'll talk mainly about 3 fast radio bursts. And the first one is this FRB called 2019-0816B, which is called repeater 3, for those who know how FRBs are called. So this was first detected by CHIME in 2019. Of course, it was also earlier seen, but in 2019, it was also seen that it was periodic, and the bursts appeared to cluster around a 5-day window with a 16.5-day period. And there were some suggestions as to what might cause this periodicity. One of them is, of course, there is some kind of orbital motion. There were other suggestions, like there could be precession of the object, and due to the precession, whenever it comes into your line of sight, you detect these bursts, and when it is looking away, you don't see the bursts, so that's precession for you. And the other one was that naturally there is an object which has a very, very long period of the order of 16 days, and that's why whenever, so you're just looking at the natural period of 16.5 days. So these were the various suggestions at the time. And so we observed this, so since this 16.5-day period was just discovered and ATEL was out, we observed it with the GMRT at band 4, which is 550 to 750 megahertz. And these observations mainly happened in the early part of 2020. So we used the GWB, which is the wideband backend, which is capable of processing this entire 200 megahertz split into 2K channels with a time resolution of about 0.3 milliseconds. And we used the telescope in what is called a phased array combination, where all the 30 dishes of the GMRT, the signals are combined, the voltages are combined, and then it is detected, which makes it a very sensitive beamformer. And we also used coherent dedispersion, which means that the voltage itself was used to dedisperse the data. So I told you about the dispersion, where the pulse arrives later at lower frequencies, and one has to correct for that when you want to detect pulses like this. So you delay the signal which comes later appropriately so that the signal lines up in time, and that process is called dedispersion. And this one has a dispersion measure of the order of 380 or so, which is very large. And so what is shown here is a gallery of bursts from these particular observations. We detected about 15 bursts in total. And you can see some of these bursts in detail. You can see the structure in both time and frequency. This is a very sharp, nice burst. And this is a somewhat wider burst, but that's because of the drift in frequency. Now, I want to draw your attention to these 2 particular bursts. This one is shown here. And this is from the simultaneous detection with Effelsberg and GMRT, that particular burst. And what you see here is actually some of these bursts, which are listed here, burst number 11, which is this one, and then burst number 13, 14, and 15, which are all here. And if you actually overlay them in a particular fashion, you can see that there is some similarity between the profiles. So one is inclined to ask the question whether this hints at some kind of intrinsic, pulsar-like object or a neutron star-like object which has a typical pulse profile. And so the 15 bursts, you can see they're all listed here. but I want to draw your particular attention to this particular burst number 9 here, which is of a very low fluence. So fluence is simply the flux density times the duration of the burst, so it's measured in Jansky millisecond, and this one is about 0.1 Jansky millisecond, which is very low fluence. And we are able to detect this at the GMRT with a good significance. Now, this is important because we are asking a question about what kind of energy does the FRB put out. So the spectral energy density, which is measured in ergs per hertz, I don't know why the number is missing. I put out, I can see that here, but anyway. So the spectral energy density here is about 10 to the 27 erg per hertz, and this is the galactic magnetar candidate, which has, whose brightest burst had an energy density of 10 to the 26 erg per hertz. So you can see that this is only an order of magnitude away. So then the question is whether magnetars can actually be considered as candidates for FRBs. And that way, I think this is interesting, and we still have to bridge. So if you consider the lowest fluence burst, we only have to bridge an energy gap of 1 order of magnitude. And so here, I talked about, in the previous slide, the 16.5-day period. So you have here the data from various other telescopes, including the GMRT, and you can see that they're all, the phase here is a normalized, so 0 is 0, and 1 is 16.5 days. And you can see that they're all falling in a narrow 5-day window here. So it's clearly periodic, but with the GMRT observations, we've been able to establish that it is indeed periodic. In fact, it was the first one that conclusively established that the period is indeed 16.5 days by looking at whether the 16.5-day period measured by CHIME was some aliased version of the actual period. And when we actually did the analysis, it was clear that 16.5-day period is the only true period. And you can see that that is given by this contiguous inactivity fraction. So that's the only way you can explain this, this figure here, that it has to be a 16.5-day period, and that was conclusively established using these observations. Now, what we also did with the GMRT is that, as you know, the GMRT is not just a beamformer, it's also an interferometer, which means that you can simultaneously make images of the sky. And with data recorded simultaneously, the visibilities, we imaged the 2 brightest bursts, which are bursts number 4 and 11. You can see the image at the time of bursting, you can see them imaged here. Of course, we did not detect any persistent emission. But what this tells you is something very interesting, which is that if you have a fast radio burst which is not very well localized, and you know only its position approximately to within 1 GMRT beam, you can actually still do this kind of a thing where you can observe the fast radio burst with the beamformer and simultaneously use the GMRT as an interferometer to localize it to arc-second precision. And I'll talk about that particular aspect in the next FRB, but we did this at the time of observation. This FRB was already known to be at this particular coordinate. So we use this as a proof of concept to establish that that sort of thing can be done. Now, the other result is, of course, this is a very interesting result. CHIME detected a secular increase in the rotation measure, which is, the rotation measure is simply defined as the, this integral where n is the column density, the number density of electrons, and B parallel is the line of sight component of the magnetic field. So it measures the integrated line of sight magnetic field strength. And CHIME saw an increase in the rotation measure. And the GMRT data at this time, is consistent with what is seen at CHIME, but we have some new measurements now which tend to point to a further increase, but perhaps not at the same rate as detected with CHIME earlier. So there's something happening clearly in the local magnetic field environment of this fast radio burst. So it's been very rapid, and now it's growing more gradually. So that's a very interesting finding, and that has implications for the immediate surroundings of the FRB. All right, so I'll move on to the next fast radio burst. This is 2020-11-24A. This is the 67th repeater. And this suddenly became very active, of course, in the first half of 2020. And there were a lot of ATELs being put out. CHIME put out the first ATEL saying that there has been a fast radio burst which has been a prolific burster, and there were other telescopes. Every other major radio telescope in the world was looking at that FRB, because it was, at the time the chime ATEL came out, it was still not very well localized. The approximate position was known, and the coordinates were such that the error was 1 GMRT beam. So in fact, the approximate position was known at the time of the observation. And since the error buzz was exactly 1 GMRT beam, we were sure that something might be detected within the GMRT beam, but we didn't know exactly where. So at the time of observations, we did not know where the exact RA deck coordinates of this FRB. But once the observations were done, all these other ATELs came out, including a VLBI localization. But nonetheless, our data at the time of observation, we did not know where to exactly point. So we had an approximate pointing. So again, this was in band 4, and several observations were done, and we had a total of about 50 bursts detected with 2K channels and about 0.6 millisecond time resolution. And since I told you that the position of the fast radio burst was not known at the time of observation, we used the GMRT as an incoherent beamformer, meaning that we use every single GMRT dish as an individual telescope and then add the detected signals. So that means that the field of view is large, which means that anywhere inside the beam, if the FRB goes off, we will be able to detect it with the beamformer. And we also simultaneously recorded interferometric visibilities to allow us to image the burst if it happened inside the beam. Okay, so those visibilities were also recorded at the highest time resolution possible at the time with the GMRT. So that's less than 1 millisecond. So I don't want to show the full gallery of bursts because we have about 48 of them, but this is just the brightest burst that I'm showing here, and it shows a lot of interesting features here. It's quite bright, and it also has this spectral march down. And here is the rate function, the cumulative rate function. So the rate function is simply defined as the number of FRBs above a certain threshold. And you can see that it's a very shallow power law with an index of 1.2. And the 10 Jansky limit, the 10 Jansky millisecond line here is the complete, which we think is the completeness limit. So below 10 millijansky second, you would not be detecting all the bursts. That's what it means. And that's why the rate function sort of flattens here, because we're missing many bursts. And just to drive home that point, here is the completeness analysis. So every single point here is the fluence of each of the bursts detected in our sample. And these lines are lines of constant fluence. And you can see that our actual completeness limit is 7 Jansky millisecond. And so all bursts above 7 Jansky millisecond have been detected. Whereas between 1 and 7 Jansky millisecond, we detected only 20%. We missed about 80% of the bursts because of the sensitivity. Now, this was done with the incoherent GMRT, which means that it's not very sensitive. But had we observed this with the phased GMRT, which we could not do only because we did not know its true position, but had we observed at this time with the phased GMRT, we would have detected a rate of 360 bursts per hour, which is a prolific rate. And it continues to be a prolific repeater, perhaps not at this rate, but occasionally it does give out a large number of bursts of the order of about, I think about 1,000 per hour has been seen in this burst. I spoke about the imaging part. So here again, since we did not know its position, we were able to image the bursts individually. So these are the brightest bursts which have been imaged, and the cross marks the position as detected by the GMRT, comparing with other localizations here, and we are sort of consistent with everybody except ASCAP. Of course, ASCAP later revised their localization, which made it consistent with the ones that you see in this picture. So what is shown here is actually the visibility data with time gaps, which have been adjusted because the bursts occurred with a lot of gaps. But you can see all these gaps now. But what we have done is taken the visibility data and de-dispersed. Typically, we don't do that. But since the visibility data was also channelized, we were able to de-disperse the visibility data and then use that visibility data to make the images of each of these bursts. And you can see them binned according to the signal to noise ratio. These are signal to noise ratio greater than, less than 10, and this is greater than 5, and this is greater than 10. So you can see that the de-dispersion really brings down the error bar. And the localized position here is consistent with other detections. And we also detected persistent emission of the order of 0.7 millijansky. So the important point that I want to talk about is, since I'm more focused on the propagation effects, I'll go through this slide. There are quite a few details here. But I want you to focus on this particular plot here. I'll come to this a little later. So what you see here is the measurement of what is called the scintillation bandwidth. Because if you look at this burst, you can see some structure as a function of frequency. Y-axis is frequency, x-axis is time, and this is the dynamic spectrum of the burst. You can see some striations in frequency. And that's a phenomenon called scintillation, which is caused by the ISM. It's a propagation effect. And one can actually measure the scintillation bandwidth at different parts of the band, and it is expected to follow a new to the 4 effect, and that is clearly seen here. So the higher frequencies were measured with Effelsberg, the lower frequencies here were GMRT measurements. The lowest frequency points are somewhat off because we believe that the frequency resolution we had at the GMRT was not sufficient to resolve the scintillation. So there might be some blending which might be leading to some of these numbers being overestimated. And we also measure scatter broadening using the last part of this burst, and we measure a scatter broadening time scale of about 13.6 milliseconds, which is actually including both the instrument effect. So the actual scatter broadening time is of the order of 11 milliseconds, which is huge. And if you look at that particular galactic line of sight, it is highly unlikely that the galaxy is causing that scattering, because from NE 2001, it is expected to scatter much less. So this scattering is certainly not coming from the Milky Way. Okay? But you ask the question, if something is so scatter broadened and it still continues to scintillate, that's very, very surprising, because something which is scatter broadened is not expected to scintillate, because it's not a point object anymore. Only point objects are supposed to scintillate. So that means that the scattering has to come from the host galaxy, which is very far, and despite the scattering, it appears to be a point source, which is why it is scintillating. And so one can use this fact to constrain where the scattering is happening. And when you do that, when you put in the information that you have from NE 2001, you expect 2 screens. One could be coming from 400 parsec, the other one could be coming from 2 kiloparsec. And if you put that number in, you get an upper limit for the host screen distance at 8 kiloparsec. So if you consider a Milky Way-like galaxy, the scattering screen which causes this scattering is supposed to be inside the host galaxy. Okay, so that's an interesting finding. Now, the other thing is, of course, whether we investigated whether there is some kind of periodicity, because we had 50 bursts, and you see that there is no periodicity here. Initially, it looks like this, so there are some points sticking out, so you might wonder if that is because of some periodicity, but it is not, because one has to scale it with the relative exposure, and when you demodulate the relative exposure time, you see something which doesn't show any special features, so it doesn't appear to have any intrinsic periodicity. Now, the other thing we also measured is the scintillation time scale, which is the time it takes for the spectrum to change completely, and you can see some of the burst spectra look remarkably similar, especially the ones which are bunched, which are closer in time. There is a lot of similarity in the spectra, and it takes a certain amount of time for that to change completely, and that's called the scintillation time scale. And this is the first scintillation time scale measurement for an FRB of the order of 8 to 13 minutes. And that also allows us to infer a screen velocity of the interstellar screen, which is within the Milky Way, of about 60 kilometers per second. So then the question is whether the Milky Way screen is at 400 parsec or 2 kiloparsec, which is the one which is causing the scintillation that we see. And one can see that if for both of these, you expect so this screen is so close to us, we expect the Earth to be able to be modulating the scintillation time scale. And this is from the initial measurement, depending on whether it is 400 parsec or 2 kiloparsec. And with extra observations here, we have been able to study the annual modulation of the scintillation timescale, and based on that, some analysis, we are able to say that it is mostly the 400 parsec screen which is likely to be causing the scintillation, and less likely to come from the 200 parsec screen. These are the posteriors for the two different models. One is a 1D anisotropic screen model, and this is a 2D isotropic screen model. Let's not get into the details of that, but both of these models are pretty close in terms of the screen distance. One is 400 parsec, the other is 460 parsec. So that's the revision of the numbers based on extra data in the next year of observations, and the points are beautifully falling on the annual modulation curve. So this is the last one that I'm going to talk about. This is another repeater, another prolific repeater observed with GMRT, which we observed in November of 2022. Again, we used both bands 3 and band 4, so 300 to 750 megahertz with just a 50 megahertz gap in between. But since the position was known, we used the phased up GMRT as the beamformer, and we also recorded baseband voltage because the VLBI mode was available, so it's always useful to record the baseband voltage, and that has some implications for what I'm going to say now. Because if you look at this burst, again, you see some striations here, very similar to what I showed in the previous FRB. And we want to measure the scintillation bandwidth. And the scintillation bandwidth was coming out to be very low, and we suspected that, again, there might be blending here, and the instrument might not be able to, the regular beamformer does not have the capacity to resolve the scintillation here. And so we used the baseband voltage, because once you have the voltage, you can resolve it into any number of channels. So the high frequency resolution allowed us to measure the small scintillation bandwidth here. So the measured scintillation bandwidth is of the order of 200 kilohertz scaled to 1 gigahertz. So at the frequency of our observation, it's even smaller. But the NA 2001 model predicts only about 70 kilohertz. But that's okay because the model is not very sensitive to small scales. And things could be changing in the Milky Way at small angles. And we also measured a scattering time scale of 0.16 milliseconds. And the distance was known to be about 300 megaparsec. And what I'm showing here is actually the the decaying exponential fits to the autocorrelation function of the scintillation bandwidth at different subbands of our observed band. And here we have a fit to the scattering, the scatter broadened pulse here, which beautifully follows the expected nu to the 4 power law. So what do we do with these measurements? Since, unlike in the case of the previous FRB, we don't have a clean, so what I meant to say is that here you can see there's these features in the Milky Way which are really screens. We don't have any such features along this particular line of sight. So we were constrained to use the 50% scattering measure as an upper limit and see what sort of distance that would allow us to constrain for the scattering screen within the host galaxy. And that turns out to be about 6 kiloparsec. And this is work done by my student Pooja Maji, who's here in the audience. And she's also concluding trying to finish some of these analyses and write up this thing for a journal. So again, here, this allows us to conclusively say that the screen which causes the scattering is within the host galaxy, and the scintillation is caused primarily by the Milky Way. So, so I'll sort of stop here and read the summary for you, just the main points, the salient points. Of course, fast radio bursts are very fascinating objects, transient. Their origins are still debated. And then there are all these repeaters that one can keep following up. But the difficulty is that only a small number of localized FRBs, so localization is something that really will up the game. And there are efforts which will allow us to answer the host galaxy connection to the progenitor, propagation effects, can be used as standard candles in cosmology. And at the GMRT, we've been following up these 3 FRBs, and each of them has its own individual characteristics, and we've been able to constrain some host galaxy properties in 2 of them. And the next frontier is, I think, multi-messenger follow-up. People have been doing that, but it's not at the level at which one would like it. Questions to ask are whether FRBs are connected to things like black hole, or neutron star mergers. And we look forward to the SKA era, doing things together with LIGO. And once we have a large number of FRBs, one can do cosmology with maybe 1 million sightlines and redshifts. So with that, I would say that the future is indeed bright for FRBs. Thank you.
Thank you so much for the summaries. We can take a couple of quick questions.
Hello, nice talk. So I have one question. So has there been any X-ray counterpart detection to FRBs?
Yeah, that's a good question. In fact, there has been a study, including the GMRT, which looked for prompt emission. There has been no detection, but there has been only an upper limit.
Okay.
So far, I think prompt detection has not been seen in FRBs.
So if there's like detection in X-rays, then it will be much easier to localize FRBs.
Well, the localization can still be done with radio. I think it will be easier to do it with radio. But yeah, possible with X-rays also, yes.
Yeah. Okay, thank you.
Okay, there's a question on the back. Can you? No, it's-
So I was wondering that you mentioned about the repeating FRBs. What are the time scales at which they repeat? That whether it's hours, days, or months?
Okay, so I don't know which particular FRB you are talking about, but in general,
Yeah.
repeating FRBs, there are only 2 FRBs which are known to have a periodicity. Periodicity is not like a pulsar's period where the burst occurs every few seconds or every few milliseconds. Rather, the periodicity of FRBs is a phase in which the FRB appears to be active, and then it goes to an inactive state. So that is at least for 2 FRBs. So one of them is the one that I talked about. It has a 16.5-day period, which means that every 16.5 days, you are sure to detect this FRB. And that FRB is continuously being studied by many groups all over the world. Another FRB, which is the first repeater, that has of the order of 150 or 160-day period. So every 160 days, it appears to be active. There are also other things which I did not talk about, which is they appear to be active at different frequencies at slightly different phases. So the 16.5-day period FRB, it appears to be active at higher frequencies somewhat earlier than at lower frequencies. So that's the kind of periodicity. And there are only 2 FRBs now with well-established periodicity.
So without the periodicity one, even if they are repeating, if they are not periodic, what is the typical time scale of the repeat?
So that is completely random. There is no prediction for that, because if one is able to predict that, that means that there is a periodicity. So one has to keep looking at these, and whenever you're lucky, you get a burst or a cluster of bursts. So the second one, which is a prolific repeater, there is no periodicity established, but if you observe it for a few days, you are sure to find a few bursts.
Yeah,
Okay,
thank
I think
you.
we should move on to the next question. Yeah, last question.
Yeah, thanks a lot for this wonderful talk. I'm curious about the magnetic field around these FRB sources. And so you showed for one of the FRBs, there's a rotation measure which has a very sharp turn. But these are integrated magnetic field along the line of sight. So I didn't get a sense of, is this sort of significant compared to like a typical line of sight, which is non-FRB at that distance? So are you saying that a significant amount of that rotation measure is within the source or in a local region in the source? And also at the population level, do we detect significant rotation measure in most of these FRB? Is there sort of a signature of magnetic field in most of them?
So I'll answer your first question quickly. So we have not, at least I have not done a systematic study of looking at a non-FRB sight line to see whether there is this is significant. But so the chime result is significant because they have a detailed paper which I also put there. So there are arguments which suggest that this has to be happening close to the FRB. Okay, and because it's a very sharp rise in the rotation measure, and that can happen over such short time scales only if there is a very dynamic environment. And at those distances, the solid angle within the galaxy which might contribute to that kind of a change is very unlikely. Now, for your second question, As a population, well, there are some FRBs which have extremely high rotation measures, but there are many FRBs which just look very normal. So there is a wide variety in that. But the ones which are really interesting are the ones with, for example, that show behavior like this, or which have extremely high magnetic fields. For example, there's one which has a very high rotation measure, and it's thought to be residing in a very dense magnetized nebula. So there are certainly cases, there's some diversity there.
Thank you. Thanks.
Okay, I think we should close the session. Thank you so much to both the speakers once again, and let's end the session.
Yeah, before we break for the tea and the poster session, 2 quick announcements. Those who have the poster displayed currently, please remember that you have to take it off